Guys, in this second video, I want to apply all the concepts we learned in our previous video in a problem about thermal circuits and thermal resistances, also with heat generation and the new geometry, that is the spherical geometry. So the objectives of this video will be to apply all the learned concepts. On the previous video, we also want to determine resistance expressions knowing the temperature profiles. We also want to apply the heat equation when resistances are not applicable. And finally, we want to sketch temperature profiles without knowing the exact solutions. So let's get started. Okay, so let's get started. This is the problem. I'll give you a couple of minutes to pause the video and maybe start the problem on your own. So the first thing that we do is list the things that we know. Most of the things are labeled in the diagram, but I wanted to emphasize that we also know the temperature profile of the fin, which was our problem for the first video. So I'm just gonna write that down. Okay, known temperature profile of the fin. We also know the dimensions and properties. Okay, so the temperature profile of the fin we obtained from the assumption that the tip was adiabatic, and as you may know in the problem it says that we can assume the fin to have an adiabatic tip, but you have to keep in mind that this is not the real case. In real life applications your tip will not be adiabatic, and even in a test you're not allowed to make this assumption unless it is explicitly said in the problem. But for simplicity purposes, we're doing it now, we're doing it here, because it greatly simplifies the temperature profile of this specific fin. But for different types of fin, sometimes you can have easier expressions for the temperature profile using an active heat loss tip. So anyway, so what we want to find is already labeled in the problem. So I won't write anything here, and then we will jump to the assumptions. The assumptions of this problem are, as usual, that we have steady state, we have negligible radiation, we have constant properties, so none of the properties depend on temperature. Properties. We also have, well, that the fin tip is adiabatic, and I think this is it. Also keep in mind that here we have a contact resistance, and the contact resistance, the significance of the contact resistance will depend on the surrounding fluid. In this case, if we have air, the contact resistance will be a lot more meaningful than if we had, say, water, because water is a greater conductor, so all these roughness effects that get filled with the fluid would hinder heat transfer if the fluid is not a good conductor. So the contact resistance depends on the fluid that's stuck in between. Okay, so now let's jump to solving this problem. Let's start with question number 1. Okay, so the first question is, what is the total heat rate? But before we develop an expression for the total heat rate, let's first take a note on the direction of heat transfer. So as you may notice in the diagram, we were given 3 different temperatures which are different radial distances from the center. This means that if those temperatures are different, heat is going to be flowing radially, from the center outwards or from the outside towards the center. So that means that our direction for heat transfer will be the radial direction. And then for the fin, we also assume that the fin was thin enough so that there won't be any temperature gradients in the vertical direction. That means that heat is flowing only in the radial direction. Now the next question is it flowing from the center outwards or from the outside to the center? And the answer is that since we have a heat sink, we have a generation, a negative generation of heat. The central sphere is actually absorbing heat from the surrounding fluid. Actually, that's the whole point of this shape of this system, is to cool down the fluid. So heat will actually flow from the surface from the outside to the center. Okay, so now that we know the direction of heat flow, we can develop an expression for the total heat rate. So the trick for this question is just noticing that at steady state, the only amount of heat that will flow in is just the volumetric heat rate of this central sphere times its volume. At steady state, you don't have any more heat going in, because imagine if more heat were coming in, it wouldn't have anywhere to go. If more heat than what it's being consumed goes in, it wouldn't have anywhere to go. So because of that, at steady state, the only heat rate that we're getting is the following. I'm going to write it down. QF. So the total heat rate is just going to be Q times the volume of the sphere, which is 4/3 by R1 cubed. So the next step is to draw the thermal circuit. Keep in mind that we cannot include material A because it has a non-constant transport rate. The heat rate is not constant since it has a thermal generation term. So because of that, we must start at the interface between A and B at T2, and remember that the temperatures are shown as nodes. So here we have three temperatures, or three nodes: T2, T3, and T infinity. Okay, so what are the resistances connecting these temperatures? The first one, R1, which is in material B, is just the conduction resistance of the sphere. So let's label it as R1. Then between T3 and T infinity, we have two resistances that are occurring. The first one is from the heat flow that is from the unexposed surface, or the exposed surface, sorry. So the surface of the sphere that is not covered by the fin is actually losing heat directly to the surrounding fluid. So that will be our first resistance. So let's call it R2. And then the other resistances are actually, well, first it is actually the resistance of the heat flowing through the fin, but that resistance is composed of two resistances. The first one is the contact resistance between material B and material C at the interface. Let's call it R3. And the other one is the fin resistance, so the overall fin resistance to heat flow. So these two bottom resistances are in series, whereas they are in parallel with the top one, with R2. Let's label them R3 and R4. And so this is our finished thermal circuit. We should also label with an arrow the direction of heat flow. So let's call this Q total. Actually, let's use different colors. Let's use red to say that a portion of that Q total will go up as Q1, and another portion, say blue, will go through the bottom as Q2. So the first resistance, R1, is just the conduction resistance within the sphere B. To derive this expression, you must start with the heat equation, and you must do a temperature definite integral between the two surfaces and the two temperatures, T2 and T3, and R1 and R2, and that way you will get an expression for the heat rate as a function of the temperature difference. You will go over this derivation in class, so I didn't include it in this video, but if you have any questions, feel free to message me. It's actually pretty simple. But so the expression for the resistance is also on your formula sheet, and it has the following form: 1 over 4 pi k times 1 over R1 minus 1 over R2. Okay, so in this case, you notice that the resistance is inversely proportional to the conductivity, and it actually is also inversely proportional to the radii. And this makes sense because as you get closer to the center, the cross-sectional area of that differential volume element will be smaller and smaller. Imagine, compare the cross-sectional area in this case of a sphere of this size with, you know, a larger sphere. The cross-sectional area being larger means you have more area through which the heat rate can transfer. So now we need an expression for R2, or the convection resistance of the exposed surface of a sphere B. And you may recall that to develop such an expression, we need to start from a equation relating the heat rate with the temperature difference, and that is Newton's law of cooling. So if we write it down here, it would be Q1 in this case, Q1 going through the exposed surface, Q1 equals H, the heat transfer coefficient, and the surface area that is exposed, let's label it as ASU, like uncovered, AS uncovered, surface area uncovered, and that will be multiplied by the temperature difference, or the excess temperature, which is T infinity minus T3, right? And here we know that T infinity is higher than T3. Okay, so from this expression, we know that the resistance, R2, will just be the reciprocal of these two terms. And that is because, as you may recall, the resistance is just the ratio of the driving force and the heat rate. So we just have to take the reciprocal of this coefficients. And now, what is the uncovered surface? Well, it's just the surface of the sphere minus the covered surface by the fin. So ASU is just the overall surface area, which is 4 pi R2 squared, minus AS, let's call it C, AS covered. And then what is the covered surface? It's just the surface of a cylinder, you know, of a really thin cylinder here at the interface between the fin and the sphere, and you can model it as a horizontal wall with length equal to the circumference of the fin, of that inner surface of the fin. So it would be 2 pi R2, right, times the thickness or the height of the wall. So the total area is just 2 pi R2 times T. And so we could insert this in this equation, but for now let's leave it like that. We already know how R2 looks like, and now we can move on to R3 and R4. Okay, so now R3, which is the contact resistance between B and C. So as you may recall, a contact resistance is expressed as a resistance per unit area, but the units are area units times Kelvin per watt, right? So in order to find the expression, we need to divide by the area. So R3 will just be RC divided by the area that is covered, ASC, which we developed an expression for here. And so it makes sense that the area is at the denominator, because the larger the area, well, the lower the actual resistance will be. The contact resistance could be thought of, you know, maybe as a resistivity in electricity, a resistivity being more a property of the material. In this case, the contact resistance is a property of this joint here. It's sort of independent of how much was glued in, or how much, or the extent of that interface. The actual amount of resistance will be determined by the area, and so the larger the area, the lower the actual resistance. Last expression is the fin resistance. So as you may recall from our first video, we developed an expression for the temperature profile, or the excess temperature profile, when the fin tip was adiabatic and when the base temperature was known. So the base temperature in this case is not quite T3. Actually, because of this contact resistance, the base temperature, we could label it as T4 here, T4. and we don't know it. We don't know what T4 is. But something great that we will discover is that resistances are independent of the driving force. We don't need to know what T4 is to develop an expression for the resistance of this fin. So this is what I'm going to show you. So here we have the temperature profile with those boundary conditions, which we also assumed to be valid in this problem. And we said that the heat rate was just the temperature gradient at the base. Well, just from Fourier's law, we said that it was just the area times the conductivity of material C, QC here, times the temperature gradient at that interface. That would be the total heat rate dissipated by the fin, right? So all we need to do is just find an expression for this derivative term evaluated at R2. So let's do so. Here I took the derivative of this temperature profile, and all you have to do is just chain rules, taking the m's out, and then noticing that the derivative of the modified Bessel function of k0 is just k minus k1. So after taking the derivative, we can plug in this derivative in the final expression for the heat rate, which we developed on the first video, and we need to evaluate that derivative at R2, or at the interface between B and C. So all these R terms, they are replaced with R2, and then they are plugged in this equation. The one of the heat, the one for the heat rate. So that's what I did here. Notice the minus sign, the conductivity, and the surface area, the covered surface area of this interface. And so to find the resistance from this expression, notice that we have related already the heat rate with the temperature difference. So this being the driving force and this being the transport rate, we have an expression for the resistance, which is just the reciprocal of the coefficient surrounding this temperature difference, or the driving force, same as in the other examples. So this leaves us with this final expression for the resistance. So something to notice is that the resistance is independent of the driving force. There is no temperature term here, so we don't really need to know what T4 is to know the resistance. Additionally, you can see that the resistance is inversely proportional to the conductivity and the covered surface area here at the interface. And you may also notice that there is an m term in the denominator, and that m term also contains the conductivity at its denominator. But since it's the square root that we're taking, overall the conductivity will be cancelled out with that square root, and you will still have a square root of kc at the denominator. So it's still inversely proportional. Okay, so the next step is to find the total resistance between T2 and T infinity. So we need to follow the rules that we introduced on the previous video, which is that resistances in series are added up, and resistances in parallel, you add up the reciprocals and then you take the inverse of that addition. So we must notice that R2 is in parallel with the addition of R3 and R4, and this total resistance of this compound resistances between T3 and T infinity, they are in series with R1. So the total resistance is just going to be R total. This is going to be R1, and it's in series with the overall resistance of R2, R3, and R4. And R2 is in parallel with R3 plus R4. So we'd have 1 over R2 plus 1 over R3 plus R4. And then you take the inverse of that. So this would be what our total resistance would look like. And now with this expression, we can find what T2 is, just knowing the overall resistance and the temperature of the surrounding fluid. Okay, so imagine if you had more than one fin, if you had multiple fins also with the contact resistance. In this case, you would actually change the number of fins here at the numerator in this equation. Say if you had 3 fins, it would actually be here 3 instead of 1, or if you had 4, it would be 4 instead of 1, because basically every new fin that you're adding it in parallel. So I think you will go over a problem like that in class, but just keep that in mind. Okay, and now that we have the expression for the total resistance, we can find an expression for T2 based on the equation for the heat rate using the resistance model. So this would be the total heat rate will basically be the difference, the temperature difference between the surrounding fluid and T2 over the total resistance, which we solved for here. And so T2 will be T infinity minus Q total times R total. From this expression, notice that as the total resistance decreases, the temperature difference between T2 and T infinity will also decrease. So that means that you need a lower driving force to convey the same amount of heat rate. And this corresponds to our definition for the resistance on our previous video. Okay, it is time now to develop an expression for T1. We were not able to include material A in our temperature and our thermal circuit. We must develop its temperature profile, and then from that temperature profile we must solve for T1. However, we already know one of the boundary conditions, which is T2, so that simplifies things. We also know the other boundary condition, which is at the center, and we know that at that point the temperature reaches a minimum, so the derivative of the temperature profile will be 0. But so to develop the temperature profile, we must start from the differential control volume, which is built by 2 patches. Imagine taking 2 patches of this sphere and then displacing them by an infinitesimal change in each of these 3 directions. So in spherical coordinates, you define any point using the vertical angle phi, the horizontal angle theta, and a radius that is pointing in the direction of these 2 angles. So by drawing 2 surfaces that are slightly displaced by a small increment in each of these directions, we end up with something that looks like this figure here. In this differential control volume, we can label the quantities for our energy balance. So we have, similar as our first derivation in the first video, Q evaluated at R, and here will be Q evaluated at R plus dr. Notice here that we only have heat flowing in the radial direction because there is symmetry to the sphere. So the only way that, well, the isotherms are basically spheres within the sphere. And we also have a heat generation. So we can just put it here at the center of our control volume. Okay, here, like this. Okay, so then when we develop the expressions for in minus out plus generation equals accumulation, we notice that accumulation is equal to 0, and then that subtracting Q evaluated at R minus Q evaluated at R plus dr from our Taylor series expansion, we just get the negative, just get the following. So we get minus d by dr of Q evaluated at R times dr, and then we also have to subtract, because in this case the generation of heat is negative, we're consuming heat, so it would be the heat rate times the volume of this differential control volume, and the volume of this differential control volume can be approximated to be the volume of a rectangle, like a cubic rectangle basically. So if we just take the product of each of these sides, we are going to get the volume of this differential control volume, so which happens to be the Jacobian d theta dr phi, and this will be equal to 0 because we're at steady state. So when we evaluate Q evaluated at R, we find that we need the temperature gradient, so d by dr, t by dr, and then we multiply it by Ka. The negative signs go away, and then we multiply it by the area at R. So at R, the area is just the area of this face here. And the area is just the product of these two sides, r sine phi d theta times r d phi. So r squared sine phi d theta d phi, and this is all multiplied by dr. Subtract sine theta and now here we can divide by our differential elements, d theta, d phi, dr, and we can also divide by r squared and by sine phi. Since sine phi is independent of r, we can pull it out of the derivative and we can cancel it out. So we cancel out this 4 terms, and all we're left with is 1 over r squared d over dr times, we can also divide by Ka because we assume constant properties. So if we divide by Ka, it will just go to it will just become the coefficient of this Q term here. So we have dt by dr times r squared minus Q over Ka equals 0. So this is our differential equation. So this is second order ODE, and for that we need 2 boundary conditions, but we already know those boundary conditions. We know that at the center we can model the center as an adiabatic point. So at the center the temperature reaches a minimum, and that means that the derivative is equal to 0. So that would be the first boundary condition, dt by dr at 0 equals 0. And the second boundary condition is the temperature at the interface between A and B, which we already know. So it's going to be T R1 will be equal to T2. Okay, so having these boundary conditions allows us to integrate this equation twice. So the first integral will be by leaving this parenthesis untouched and then integrating the whole equation. So when we do so, we will get dt by dr times r squared will be equal to Q over Ka times r squared, and the integral of r squared is just r cubed over 3, right? And then we add an integration constant, C1. And so to solve for C1, we need to evaluate this first boundary condition. So we know that when r equals 0, C1 has to be 0, because if r is equal to 0, notice this goes to 0, this goes to 0, and C1 must be 0 to keep this equation true. So C1 equals 0. Okay, and now we need to integrate it once more. But first we need to divide by this r squareds. So when we divide by r squared, this becomes an r, and then when we take the integral, we end up with, I'm going to write it down here. So this is the final temperature profile. Q times r squared, because we canceled out the r squares and then we were left off with an r, and then the integral is just r squared, and the 2 in the denominator multiplied by 3 gives us a 6 Ka, and then we add a new integration constant called C2. To solve for this integration constant, we need to use the second boundary condition that said that T2 was the temperature when we evaluated this temperature profile at R1. So to solve for R2, we get T2 is equal to Q R1 squared over 6 Ka plus C2, or that C2 will be equal to T2 minus Q R1 squared over 6KA. Let's continue on this new tab. So we had, let's plug in our integration constant. So we had that it was equal to Q times R squared over 6KA plus C2, right? And plugging it in and taking a common factor of the Q and the 6KA, we end up with T equals T2 plus Q over 6KA times R squared minus R1 squared. So as you may notice, R1 squared is larger than any R evaluated on A, on material A. So we can take out this negative sign and put it here in front as follows: T is T2 minus Q over 6KA squared minus R squared. Okay, so now we are almost done with the problem. So now to evaluate the temperature at T1, we must evaluate this temperature profile when the radius is 0 at the center. So when the radius is 0, this last term here, T of 0, this last term here goes to 0. So T1 equals T1 equals T2 minus Q over 6KA times R1 squared. So this is basically the temperature we were looking for, or the coolest temperature, and the temperature of the surrounding air is included in T2, which we solved for in our first question. Okay, so the last step to this problem is sketching the temperature profile. So when, all sketching comes down to is your boundary conditions. We'll start with with material A, for which we know the two boundary conditions and we also know the temperature profile. So the first boundary condition was that we had an adiabatic center, so that means that the temperature at this point has a 0 slope, which we illustrate by a dashed line, a vertical dashed line, a horizontal dashed line. And then we also know that at R1 the temperature is T2. So we have our starting point and our endpoint. We know that T2 must be higher than T1 because the fin is absorbing heat from the exterior. So the lowest temperature is at the center. And then from our temperature profile, we know that the evolution of temperature is a quadratic evolution. So that means that your slope will increase linearly with the radius, or that your or that the profile is concave up, sort of like a parabola. It's a parabolic shape. Let me just redraw it better. Sort of like this. And so, yeah. Okay, so then after we reached the interface, to know how the temperature profile looks like in material B, even though we didn't solve for the temperature profile, we can guess, or we can show how the sketch would look, or the shape, based on also the endpoints. So we know that the first point was T2, and the next point is T3, which we don't necessarily know, but we know that must be higher than T2. And then to know the shape of this curve, let's say T3 was here. To know the shape of this curve, we must refer to Fourier's law. So between R1 and R2, Fourier's law tells us that the total heat rate, Q total, is equal to minus the conductivity of material B times the temperature gradient times the cross-sectional area. And the cross-sectional area of a sphere is 4 pi r squared, right? And so this means that if we want to preserve a constant heat rate, we must either change the gradient or the radius. So that means that at the lowest radius, at R1, our gradient has to be the maximum within this material. And as we get further from the center, the gradient decreases at a squared proportion as the radius increases. So that means that originally the slope will be higher slope, but then as we reach, wait, I don't want it to look like a zero slope at the end, because the slope is not zero at T3, sort of like this. So it gets harder for heat to flow as you get closer to the center, because the cross-sectional area gets smaller. But as you get farther from it, the cross-sectional area increases, allowing more heat to flow with a lower driving force, with a lower temperature difference. Okay, so now between T3 and, well, at R2 there is a contact resistance between the fin and the sphere, and the contact resistance is expressed as a temperature drop at the same radius. So I'm going to draw it as black, and we can label this as T4, and there is a contact resistance at the interface, and it occurs at the same radius, but this is part of material C now. Okay, so for the fin, we have two boundary conditions that we used and that were specific for this problem. The first one was that we knew the base temperature, T4, and the second one was that we knew that we had an adiabatic fin tip. So by adiabatic, we're just saying that the slope at R3 at the tip was 0, which also tells us that the temperature then has to be equal as the temperature of the surrounding fluid. Here is where we get to see really whether we made a mistake by assuming a adiabatic fin tip, because if the fin is not long enough, then that means that your temperature at the edge might not be quite the same as your surrounding fluid, and you will actually have some heat loss at that point. Please remember that we are just plotting it like this in this case because these are the boundary conditions that we used, but in reality and in a test you're expected to have the right boundary conditions, which are that at the fin tip you have some heat loss. But so here the temperature profile behaves similarly as for the sphere. Your heat rate will actually be the highest, or your temperature gradient will be the highest at when you're closer to the center, because as you get farther, more surface area will be exposed, and so the temperature of that surface area will be a lot more similar to the surrounding fluid than closer to the center. So because of that, at first you have a higher gradient, and as you get farther it slowly plateaus till it becomes 0 at R3. Let me draw it better, sort of like this. And when you're sketching, you don't have to be exact. You just have to hit your boundary conditions. So please always remember to start with your boundary conditions. You know, if it's a temperature or if it's a slope, label them before and make sure you understand them. And then once you do that, it's very easy to fill the gaps. You know, here we knew the starting point and the slope at the end point, so it just makes sense to sort of connect them by realizing that the gradient has to decrease as you're increasing your radius. So then the temperature for the surrounding fluid will be the same as the temperature at R3. So we show it like that. And again, remember that in a test you're expected to show heat loss at the tip. Okay, so we reached the end of the video. We were able to apply the learned concepts of thermal resistances in circuits. By doing the example that we just did, we were also able to find resistance expressions knowing the temperature profile, which we did for the fin. We were also able to develop the heat equation when resistances were not applicable, which was for material A. We were also able to sketch the temperature profiles without knowing the exact solutions, as we did here. We just knew a couple of boundary conditions, and the way that resistance has evolved as the radius increased. So thank you very much for watching, and if you have any comments or remarks, please let me know in the comments or send me a message. Thank you.